Hi everybody, welcome to another UK Metamaterials Network Colloquium. I'm Alistair Hibbins, I'm PI of the Metamaterials Network and the Exeter Centre of Metamaterials Research and Innovation, which is where the talk is taking place today. Our speaker is Dr. Tom Allen. Tom is a senior lecturer at Manchester Metropolitan University. He's a sports engineer interested in the role that engineering and technology play in terms of performance, injury risk and participation. He's a fellow of the IMechE and a board member of the Biomedical Engineering Division as well. He's collaborated with a host of different sports brands and is an enthusiastic science communicator as well. So, for example, you might have seen recently how he contributed to the discussion of the role of footwear in improving performance in athletics, and I think you might be speaking about that later on. So I'm sure we'll hear, as I said, much more about that over the next 45 minutes or so. So over to you, Tom.
Thank you. So thank you for the introduction. As you've heard, I'm Tom, and I'm going to be talking about metamaterials for sports applications. There we go. So this is the structure of my talk. So I'm going to start off by giving an overview of the work we do in sports engineering, an introduction to that field, then the work which we've been doing in Auxetic materials, and then finally bringing that together and talking about the opportunities to bring these areas together. So that's Auxetics and metamaterials in general and the sports communities. So first of all, what is sports engineering? So engineering is about solving problems, using a good understanding of physics and maths and the application of technology. So that's exactly what sports engineering is, except we're solving problems within sport. For example, how to help this person vault higher, or how to reduce their injury risk when doing so. So I'm interested in the effect of technology on sport, and this distills down into three main areas. So we have performance, participation, and prevention, and that's prevention of injuries. We can work with different organizations to look at different problems. And one of the nice things about the sports sector is it tends to be rapid uptake. So it's a good place to test and explore opportunities for things like metamaterials and to explore manufacturing. And then this can then feed into other industries afterwards. So it's an ideal test bed. I work with different organizations and I'm on different committees. So I'm on the committee for the International Society for Snow Sports Safety. That's all about reducing injuries in snow sports. I'm involved with the Biomedical Engineering Division, so the committee of the IMechE, and that is where sports engineering fits. But sports engineering can also feed into health and recreation as well. I'm on the BSI committee, protective equipment for sports players. So that gives me a really good understanding of the role of protective equipment and how we can regulate and certify that. I'm the editor of Sports Engineering Journal, and I'm also the lead editor for the next Routledge Handbook, Sports Technology and Engineering. So that's going to be the second edition. My work typically involves experimental mechanics and modeling to understand the performance of sports equipment and associated materials. And we often use high-speed cameras, as you can see here. This example is for a tennis racket, and we can really use these cameras to look at this in detail and understand how the ball and the racket interact and how the racket vibrates after impact. I have a couple of examples here. The one at the top, you can see the impact position is lower down and the racket is vibrating more, whereas the one in the second image underneath, we're impacting more towards the center or the node point, so we have fewer vibrations of the racket. And then we can look at other concepts such as a center of percussion, where the force is translated through the hand and you get less jarring effect. So that's just a few examples of how we use high-speed cameras. So this quote was taken directly from the Olympic Legacy document. And as a sports engineer, I can work with many different groups to benefit many different people. So we can have the next generation, which we're trying to inspire, and the teams who are inspiring them, as well as the athletes. The organizations that are making the equipment which they're using, but also the governing bodies as well. So the ones who set the rules, ensure the game is fair and the injury risks are low and athlete welfare is really considered. And museums such as the Wimbledon Lawn Tennis Museum, where we can go and we can characterize things like old rackets, and then feeds into education. And then research organizations as well, such as the UK Metamaterials Network. So there's lots of opportunities in sports engineering. As I was saying before, it's a rapid uptake sector. So it's a good place to test and try on new materials and bring them into products. And I'll be talking about some examples of that as we go through. So now talking about sports engineering specifically, these are some of the areas I'm going to talk about. So the work we've done on wrist protectors. So we've developed the first standards, that's an ISO standard for snowboarding wrist protectors. Rugby padding, so working with World Rugby to update their regulations for body padding in rugby. Running shoes. So this is where we're looking at the degradation of shoes and how that can affect performance and injury risk. And then tennis rackets. And I'm giving an example of the work that I've done to implement auxetic materials into tennis rackets with my partners. So first of all, wrist protectors. So we're working with the International Society for Snow Sports Safety and the BFU, which is the Swiss Council for Accident Prevention, to develop a standard for snowboarding wrist protectors. So wrist injuries are really common amongst snowboarders. As you can imagine, you've got your feet strapped to the board. If you fall over, your natural instinct is to put your arms out, and then you can fracture your wrist or to fall backwards as well. Around 30 to 40% of all injuries are to the wrist. There are wrist protectors available, but most people don't wear them. And before we started working on this project, there was no standard. So we developed this test. So I'm working with Nick, who's at Sheffield Hallam University, Caroline and Keith. So Keith and Caroline working with me at Manchester, but Caroline's now at the English Institute of Sport. And she developed this rig as part of her PhD. We can see we can simulate this very harsh impact down onto the surrogate wrist, and we have the wrist protector fitted as well. We can measure the angle of the pendulum, the force transferred through the wrist, and the angle of the wrist as well. We can use advanced techniques such as digital image correlation. So we have a pair of stereo calibrated cameras. We have a speckle pattern on the back there, and you can see that we can measure the displacement. And we've done lots of different iterations, particularly involving developing the surrogate, which we're testing with, so the wrist, to make it more realistic or more biofidelic. And this led to the development of this new standard. Now that we have the standard published, we're moving into working with the manufacturers to ensure their products are certified to that standard. Working with the different organizations, such as the snowboard schools and the BFU, to raise awareness of the wrist protectors amongst snowboarders, and then ultimately to document injuries. And then this will then all feed back to a future revision of that standard. So we're continuously monitoring what we're doing and then looking to improve. In similar work, we're working with World Rugby to develop standards and regulations, so to review their existing standards for body padding. So rugby players often wear body padding, particularly on their shoulders, and that is to prevent cuts and abrasions to soft tissue. It's not to prevent severe injuries such as dislocations and breaks. That's a common misconception. So that's World Rugby's intention, and that was something that we had to really consider when reviewing these regulations. Similar to with the wrist protectors, we built a surrogate, like you can see here. So this is a basic surrogate to represent the shoulder. We've got a steel hemisphere covered with a soft tissue simulant and then a skin simulant on top of that. Like I was showing before, we can do testing, so experimental mechanics. Here we've got an impact test coming down. So that's on one side, you can see, and then on the other side, you can see we can angle that plate and we can look at different scenarios. We can put padding on top. We have load cells underneath, so we can measure the force, just like we were with the wrist protector, and we can film with a high-speed camera. And here's a couple of examples. This is the work of one of my PhD students, who's at Dill, my collaborators at Sheffield University. So you can see we've got the impact on one side with the high-speed camera, and then the model on the other side. And the idea is we can then use the model to explore different opportunities for padding, which could involve metamaterials. And some different scenarios here that we're looking at with the model. Just a couple of examples. One, we can look at the effect of placing some kind of protective material on top, and then we have a raking scenario underneath. And this led to the update of the body padding specifications. So just like we're doing with the wrist protectors, it's now about working with the different organizations that make this padding to ensure their products become certified, documenting the number of certified products on the market, how often they're used, and then how this affects injuries, and then continuing that cycle of updating and then improvement. And some things that we've done, what's important with these regulations is to ensure they're not restrictive, so they don't stifle innovations, such as the application of metamaterials into these products. Another example here is some work I was doing with my students on running shoes. So we're looking at the degradation of running shoes. So running shoes would be used in a marathon, for example. You might run for several hours and the shoe properties could change, particularly if you're doing that over a sustained period of time. So if you're running marathon distances while you're training over a long period of time, the shoes can degrade. So we have a test here where we can mimic that. So this is filmed with a high-speed camera. We can compress the shoe many times, see how the properties change over time. Once we have the test set up, we can then explore different solutions, which could be improvements to material or using structures rather than foam. And that can have implications for both performance and injury risk. And the final example from sport is with the tennis rackets that you see here. So we're interested in characterizing how the tennis racket has changed. So how the tennis racket has changed since the origins of the game and the influence this might have had. This is myself and Luca. We're very lucky we got to go to the Wimbledon Lawn Tennis Museum. Luca's there measuring the balance point, and I'm measuring the moments of inertia. We're measuring lots of rackets, so as you can imagine, we had to have quite slick techniques to go through, but also ensure it was rigorous as well. So I'm not going to showcase all the results. What I'm going to do is showcase the results which are most applicable to the metamaterials. So what we have here, we have a data point for every racket. So we've got over 500 rackets. They're color-coded by color. So we have the wooden rackets, you see in brown, which is the older rackets, and then the composite rackets, which are blue. And then we have some other materials in between as well. So the first graph we can look at is the frequency against year. So the frequency is how fast the racket is vibrating. For a higher frequency, for the same mass, we can say that the racket would be stiffer. So the old rackets have a constant value of around 100 hertz. And then we see this transition in the sort of 60s, 70s, and 80s to new materials, particularly composite materials, and we see this increase in the frequency of the rackets. So if they were the same mass, the modern rackets would be vibrating faster. Then we can look at damping ratio against year. What's quite interesting here is you can see that the old wooden rackets actually have more damping than the modern composite ones. And that seems like maybe the rackets have got worse. That's something to think about. What's really interesting is when we plot damping ratio against frequency, and we see some clear groups. So we can see the old wooden rackets have high damping ratios, but low frequency. The metal rackets and the other materials have low damping and low frequency, and that's bad, and I'm going to explain that in a minute. And I think this plot explains why metal isn't used in these products and other similar products. And then for the composites, we have high frequency and low damping. So if we look at the example of vibration traces, we can see the wooden racket has relatively low frequency, so it vibrates relatively slowly, but it has high damping. So from one vibration to the next, it's decreasing quite a lot. Then we look at our other extreme, which is the aluminium racket, has similar frequency to the wooden racket, but much lower damping. So it's vibrating slowly, only decreasing. It takes a long time for those vibrations to decay. So you'd feel that through your hand if you don't hit the ball well, and that's not good. So the player wouldn't like that. Whereas when we look at our composite racket, even though it only has low damping ratio, it has a higher frequency. So it's vibrating quicker. So even though it's only decreasing a small amount from one vibration to the next, because it's vibrating quicker, the time isn't so long. So we can see it's not actually too bad, but there's definitely room for improvement. I'm going to talk about that in a minute. But we published this work in open access and MDPI, Applied Sciences. And one of the key things here is we were talking about the potential to use auxetics and other advanced materials to overcome some of the problems that we saw. And that's exactly what I did. So myself and Andy, who I work with very closely on the auxetic materials, we approached the tennis racket company head and we talked to them about the idea of auxetic composites. We showed them that you can make auxetic composites using the conventional materials which they would use by just laying up the composite layers in a different way. This was something they were interested in, particularly when we explained that that can have an improvement in the vibration damping. That's one of the key benefits of auxetic materials. And they liked this idea. We worked with them, and then that led to a range of tennis rackets, which are now on the market. And now we're really looking forward to continuing to work with them to realize, the full potential of these materials and also to really understand some of the potential benefits. So now I'm going to talk about the work we've been doing in Auxetic Materials. This is some of the people in the team that I work with. So we have Todd, who's doing this as part of his PhD, Keith and Ollie, who I work with in Manchester, and then Andy, who's a professor of smart materials and structures at Sheffield Hallam University. Andy and I started working together about 10 years ago, and we've been really doing a lot in this area to bring together his area of smart materials and my area of sports engineering. And that's what I'm going to be talking about now. So many of these materials, it's related to the structure of the material that gives them the unique properties. So we have the auxetic foam on the end here. So because of the specific structure, which I'm going to talk about in a minute, when we pull that, it will expand. And then we have one of Ollie's structures, which he's currently working on in the middle. This is a 3D printed structure, but this animation here is from a model. So he gets a specific design for the structure, which causes it to twist when you compress it. And this twisting can increase the indentation resistance. And that can give some desirable properties that I'll talk about soon. And then on the far side, we have a 3D printed structure. So that's an auxetic structure. You can tell because it's coming inwards. And that's one of Todd's structures. The difference between this and the foam is because it's 3D printed, we can fine control the design of that structure to get the properties that we want. We can look at different structures, and we can vary different things and look at gradients. And I'll be talking about that in a minute. So first of all, this is a definition of Poisson's ratio. A conventional material, when we pull it, will contract with an auxetic material, will fatten and expand. So it's counterintuitive. There's different ways of achieving this. It's often related to the structure. This is one of the PhD students' work that Andy and I supervised. And here we're looking at rugby padding. We've got conventional foam, but we've cut this specific pattern into the structure that you can see here. So this pattern, when we pull it, causes it to expand and have those auxetic properties. Quite interesting, when we were working on the rugby project, we actually saw some auxetic patterns in the rugby padding, which we were cutting out of the jerseys and looking at. So that's the way that they were shaped. So why are we interested in this? Well, negative Poisson's ratio can be a route to enhancing other properties. Got a couple of examples here. Indentation resistance to start with. So if we look at this equation here, and we assume that everything else is constant, for an isotropic material, we get a wider range in Poisson's ratio. And if we can get Poisson's ratios down as far as -1, then in theory, our hardness or indentation resistance will tend towards infinity. That's interesting from a theoretical perspective, but from my perspective as a sports engineer, it's, well, can we actually produce materials which do that? And can they work in that fashion over the full strain and strain rates and scenarios which we're interested in? So that's the real challenge. And then we have curvature as well. So our conventional material, when we bend it, it will saddle, and that's at the top. Whereas our auxetic material, that will form a nice dome shape. So we call that synclastic curvature. And there could be some benefits there. So it could fit inside a helmet or a knee pad or a shoulder pad in rugby. And there's some examples already of this, which I'll be showing. This is one of Ollie's videos showcasing the indentation resistance. So these are open cell auxetic foams. We've got a range of Poisson's ratios going across here, and we're indenting them with a cylinder. So the cylinder, imagine, goes back into the screen and coming down. So it's a long cylinder on top of a cube. And we can see the auxetic material is coming inwards, as we would expect, and densifying underneath that material. The zero Poisson's ratio is coming straight down, and the one on the end, the positive Poisson's ratio, conventional material, is coming outwards. So why is that indentation resistance important? Well, many athletes don't actually wear protective equipment because it might be too bulky or heavy. Typically, you'd have some kind of foam with a rigid shell on top. If we can get that indentation resistance from the material itself, then we might not need that rigid shell to go on top. It could be lighter, more breathable, more flexible. So a real challenge is not just making the equipment which works, it's encouraging people to wear it and think about the barriers of why they don't wear it. So we can have auxetic materials in nature. We've got some examples here. And as I was saying before, they're also starting to emerge in sports equipment. So in the middle is a tennis racket from Head, which Andy and I worked on. So that's based on the auxetic composites. And then we have some other examples as well. We have some running shoes. So in green, we have the Under Armour running shoe. You can see that classic bow tie structure, the very classic auxetic structure there. And what's interesting about this is that it varies across that top of that shoe. So you can have different properties in different places. But I think the idea of this is it can be quite tight Then you put your shoe in and it will expand and fit to the areas where you want it to fit. And then we have the Nike shoe underneath. You can see the sole, you can see the structure is cut through that, so that will bend and move in a certain way when you bend it. And then we have the Puma shoe, where we have the structure going through. One of the things you'll notice that many of these examples are based on the structure of the material, rather than the material being Auxetic itself. And then we have an example at the top there for a knee pad. Exactly what I said before, it forms that nice dome shape. And that's the benefits that we're having here. And you can see from that as well, it's relatively similar in shape and concept to the Under Armour shoe underneath in green. So I'm going to talk about the work we've been doing on Auxetic foams, and that's some of the key publications to do with the sports area that we published. So first of all, we need to make the foam. We've actually been able to do this for a long time, right back to the late 80s. But from the sports engineering perspective, it's more about, right, how do we make it more consistent, mass produce it, and test it in large samples. But we take our conventional foam, we have a conventional cell structure, then we need to compress it to get this reentrant cell structure, because when we pull that reentrant cell structure, it will expand and give it that negative Poisson's ratio. So we can squash it into a box, we can use some kind of pressure. There's different ways in which we compress it. And then we need to fix it as well. So we could place it in an oven so it softens, and then take it out of the oven so it hardens, or we could put it in some kind of chemical bath that causes it to soften, and then take it out. So we're basically changing the structure and then setting it in that new structure. Typically, we would use thermomechanical. And I'll just give an example here. So we take a cube of foam, for example, squash that into a metal box, place it into an oven, and then take it out of the oven, let it cool in the box, and then we have our Auxetic foam. Relatively straightforward process. You can see here, we've got the metal molds, and this is purposely quite straightforward because we wanted to do this in our labs and be able to demonstrate it. As I was saying before, the real challenge is how do you take something like this and upscale it into a product? So we have our unconverted foam, and then we have our Auxetic foam, and you see those kinked cell ribs. So we've compressed it, changed the shape. When we pull it, those ribs will straighten. We can do different testing. So we can have quasi-static testing, where we might compress it between two plates, or pull it, film with a camera, check that Poisson's ratio, also dynamic testing as well. I think that's one of the areas that our group's quite good at. It's a dynamic testing, because that's where it really applies to sports equipment. It has to actually work in the area where it's needed. So some examples from some of our earlier work, where we have a tensile test, and we have some pins in there. So as we pull it, we can track to see if those pins are expanding and measure the Poisson's ratio. And then we have a compression test, where compressing and contract, see it's contracting. We've moved away from that now, and we tend to do more full field strain measurement with digital image correlation. And I'll show you some examples of that as we go through. We can look at our stress strain relationships. So the force that we're applying and the amount that it's compressing. And we can see for our conventional material, we have that expected plateau region. Whereas our Auxetic material, because we've already compressed it, we see a much more linear stress strain relationship. And this is related to the cellular structure, as I was saying before. We can do tests where we're mimicking sports equipment. So we can have our foam, and then we can put a thin plastic shell on top, like you would have in a shin pad or a back protector or some other form of body armor. And we can look at our force displacement relationships. And you see we have quite different curves compared to the Auxetic and the conventional. The Auxetic tends to be much stiffer, and that larger hysteresis loop as well. So there's more energy within that curve. What we're really interested in is dynamic tests. You can see here. So we're dropping a mass down onto our foam. At the top, we have our sample of foam. These are open cell foams. That's unconverted, thin shell on top to mimic some kind of body armor, and then a hemisphere made of steel coming down on top. And then underneath, we have our Auxetic sample. We have the marks on here, you can see as well, so that allows us to track it. Again, this is relatively old, and now we're using more full field strain measurement. And you can see for our unconverted, offers very little resistance to that dropper. And you can see the dropper is pretty much striking against the table. The Auxetic is coming in exactly as we'd expect, preventing it from striking against the table. So when we look at our acceleration time trace, because we have an accelerometer embedded within the drop mass, we can see for our unconverted, we have that very short, sharp increase in acceleration. So that would be bad. That would be related to some kind of injury risk. So we can see that. And then when we look at our Auxetic material, we have a much flatter, that's in black, longer, pronounced acceleration time curve. And then our other material in blue, which is the intermediate, so might be closer to to a 0 Poisson's ratio is somewhere in between. So exactly as we'd expect. And what we do is we combine the raw data with the high-speed camera to give us a really good understanding of what's going on. Once we understand, we can then start applying it. So now I'm going to talk about closed cell foam, because what I've been talking about before was open cell foam. It's very easy to work with, very easy for us to do our experiments with. But the problem with that is it doesn't really apply to sports equipment. Maybe in some kind of comfort layer in the helmet or padding in the upper of the shoe, but not so much in performance applications, like within the running shoe, and in the midsole. So we're interested in closed cell foam, which is much stiffer. It's stiffer because the air is trapped within the cells. So when we go to compress it, it can't just come out of the cell like it does with the open cell. But that also makes it harder to work with, because if we were to use the same process and just compress it and heat it, we would essentially just burst the cells. So we need to look at other ways of doing this. So there was this paper in 2018, and Ollie's made a nice animation to explain this. Essentially what we do is we steam the foam. So this is just water. We put it in the oven and we steam it in a steam bath. The water goes into the cell and that causes it to contract, as you'll see here. And as it dries, you're then left with that reentrant cell structure, which gives it that negative Poisson's ratio. So we got inspired by that original publication. We then took this and did our own publication. And what we're doing, because we're more on the applied side, is taking that and saying, okay, that's a nice idea, but how does that affect the parameters? If we change the different parameters, what's the best way to make it consistently, make it in larger samples? So we published on that. And then we had a follow-up publication as well, where we're looking to see if we can manipulate the properties of the foam during that process. So if we were to place pins within the foam, could we stretch it in one direction whilst contracting it in another, and getting very kind of distorted or elongated cells, which would give extreme properties? Or maybe one bit would be steamed and one bit wouldn't be steamed, and then we can have negative and positive Poisson's ratio in the same part of the material. And then that allows us to look at gradient structures. So here's some examples of this. So that there's Ollie and some of his images across the top of the cellular structure with various amounts of contraction or reentrant structure. So you've got conventional, the normal cell structure. And then underneath we have the video, which is playing. So this is what I was saying before. We're using the full field strain mapping now, rather than just mapping those discrete points. So our conventional, you can see, is behaving as expected. Our auxetic is also behaving as expected. And then we have our gradient structure. So half of it might be auxetic and half of it might be conventional. And that's because half of it has been exposed to the steam bath and the other half hasn't. It's relatively straightforward. Again, we're more interested in moving towards production, having this in actual products, and that's quite hard to achieve using a process like that. So what we're looking at is a pressure vessel, and this goes back to 96, a relatively old method. We've been meaning to do this for a while, and one of our technicians at the university really helped us with this, because it came up with this very simple design for a pressure vessel, and we're using off-the-shelf components. So it's low cost, simple to put together, and crucially, we don't have to go out and get it certified, which adds extra cost and uncertainty, because obviously taking a pressure vessel and putting that in an oven is quite a dangerous thing to do. So this comes pre-certified, bolts together, and we put a little valve in it, and we can pump it up with a bike shock pump. So it's very simple, straightforward process. And then we have a thermocouple inside to measure the temperature. So we put it together, put the foam in, place it in the oven, and it's a similar process before, but except this time we're applying the pressure with the pressure rather than contracting it in a metal mold. This diagram here that Ollie put together just explains the process of pressurizing, softening. And then what we found was there was an extended period at the end where the foam would be settling and maybe slowly expanding or changing or contracting at the end of that process. And that was quite slow. That actually lasted for several weeks, where Ollie would be continuing to measure the properties. One of the things that we found was if we put it in a vacuum chamber overnight, that accelerated the process, and then the next day the foam had settled. And it's probably possible that it would actually settle much quicker. We just did it overnight and then we checked it in the morning and it was fine. So that all went into that publication. So our work is about how do we take these methods and then streamline them and say this is how they could be applied. And we're working with different partners in this area as well now So that includes the Fraunhofer Institute and sports companies to really apply these. This is some of the results, again, from the digital image correlation. You can see here, as we're pulling that sample, that's the Auxetic sample, it's expanding exactly as we would expect. And then we have our two samples on the other side. One is the processed or the Auxetic sample, and you can see that it's contracting, and then the conventional sample is expanding. So these materials are behaving as we would expect, because obviously we need to make them, and then we need to check that the properties are as we expect. Let's play that through once more. You can see we've got that speckle pattern which we apply to the surface, which allows us to track it. Some of the other stuff we've done as well is actually measuring the Poisson's ratio under impact and in dynamic scenarios to check that it actually transfers, because that's important, and also transfers to the strain magnitudes that we're interested as well. So here's some of the work which Ollie did with the final year students, and you can see we've got force against times. This is an impact test. We have one where we have a hemisphere, and you can see for the unconverted foam, so the conventional foam and the Auxetic foam, we have a relatively similar trace. Whereas when we look at our stud impact, so a concentrated load, we see that the Auxetic has a lower peak force. That would be lower injury risk or lower force transferred to the person. The reason for that is as we'd expect, because it's coming in and it's contracting and providing the extra indentation resistance linked back to the theory that I was talking about before. So this is important because it means that we might be able to remove the need for a rigid shell on top of the protective equipment, so more people would then use it. And we might be able to have a gradient structure as well. So we could have very high indentation resistance at the top, maybe lower underneath. So now I'm going to talk about some of the work we've done rather than working with foams, but 3D printed or additively manufactured structures. This was the work that Todd was doing. This is one of the papers that he published. So here we can see we've got a computer model. This allows us to design the structure, and then we have a 3D print, which is printed directly from the geometry of that model. The advantage of this is that we can finally control the structure, so we can get the exact properties that we want, and we can manipulate and change them. One of the things that you'll notice is that these structures are relatively similar to those which we've seen in the sports equipment, particularly the Under Armour shoe at the top and the knee pad underneath. So we print these in the university on the 3D printer, just a low-cost desktop printer using the TPU NinjaFlex, which is a very flexible material. And we just print it out like this, takes a couple hours, and then we have a prototype which we can test. So we have our model, we have the prototypes, and we can go through that cycle of testing and modeling. We can test it under impact. So we have a drop rig here, so we have a mass coming down on a rail. We have load cells positioned underneath the sample, and then we're filming with a high-speed camera. And it's all synchronized together. So for every bit of force, we can have a corresponding image as well. And it helps us to understand, because we're creating a model, we need the material properties. So you can see here, we've got a 3D printed disc. We can compress this between the plates. We can do that at different strain rates. So we have strain against stress in this plot, so the amount we're compressing it and the force to compress it. And we compressed it slowly in the machine, and then we've also compressed it under impact. And we see that we have much higher stiffness when we do it under impact, so it's rate dependent. And what we actually used was the properties from when we were doing the impact test. Then we have our stress relaxation test on the other side. So in this test, we're compressing it, we compress it very quickly, and then we hold it and look at how the stress changes over time, or the force to hold it. And you can see there that it's decaying. So again, that shows that it's rate dependent. And we put these into our model. And these are some examples here. So underneath, we have our structure, and we're impacting it in our test and filming with the camera. And then across the top, we have our models. And the idea is that we check the model against the experiment. If the model and the experiment agree with each other, we can then use the model as a design tool. This example is for a flat face dropper, but we've also done work with other shapes, including a hemisphere that you can see here. And again, this is where that indentation resistance in the Auxetic material, the advantage can really come in. And as you can imagine from looking at those shapes, there's different advantages and disadvantages of using those different types of Auxetic structures. And these are just some of the examples we looked at. You could have a gradient structure. You could have different material properties in different places. So these are the types of results which we'd get. So we have force against time, similar to before. So we have load cells underneath the sample. We've got different colors corresponding to different drop heights or impact energies. And you can see we have the flat and the hemisphere. We have reasonable agreement between the model and the experiment. The agreement was sufficient for us to then use that as a design tool. Underneath, you can see a snippet from the model, and you can see the mesh which Todd's applied. And the reason why I've included that is just to showcase the level of detail that he went to get that mesh right, because that's really important to ensure the results are correct. And just another example here of a structure where we have more elements within that structure. So it's more like a continuum material. This is some of the things which we can see. And we can see that as it contracts in, confirming it's auxetic. So this feeds into the final part on auxetics. So we were working with Loughborough University to develop a 3D printed socket with an auxetic liner. So going back to what I was saying before about encouraging the whole population to be more physically active, and this includes children who use prosthesis. And here's an example of the design that we came up with. So this was funded by the StarWorks Network, which is NIHR. So it's about bringing together academia, industry, and the NHS to help solve some of the problems that these children face in their everyday lives. This was a concept that we came up with. So Loughborough were working on the socket itself, so the 3D printed socket using 3D printed composites, and then we were working with the liner. So this is just some of the early concept designs, and this is what we came up with. So it was Simon, which I was working with in Loughborough, and we're still working together now on a redistributed manufacturing and healthcare network project. But the idea is we've got the 3D printed outer and the 3D printed socket liner as well with an auxetic material, which can contract and move to conform to the individual. So that could be due to changes in size throughout the day, so short term or long term as well as they grow. At one of the StarWorks meetings, there was an illustrator who was sketching the different projects. And this is what they came up with for our project, which I think really sums it up well. It's all about smart materials and 3D printing and bringing those things together. And we're now working together, as I was saying before, to bring this up to technologies readiness levels. I think we're around about 2 or 3 at the moment, and we're hoping to get more towards production and then bringing this onto the market to have some benefits. So just to kind of conclude this bit now, this is some of the work which Ollie's doing, looking at these twisting structures. As I was saying before, you could argue these are auxetic because they contract in, but it's more about this novel idea of the twisting, which Ollie's implementing here. And then he's shown that they're getting increased indentation resistance. So I'm going to conclude by talking about some of the opportunities to bring these different areas together. So that's the area of sport, the area of metamaterials, bringing them together to see what advantages and opportunities there are. So we've already talked about the tennis racket. You can see the image underneath. So we had wood, we transitioned to composites. Maybe this is the next iteration of composites looking at auxetics. We're already working with head. There's lots of opportunities there to continue, but we can think about other products which are made from composite materials. So skis, snowboards, bike frames, protective equipment. We have carbon fiber plates now in running shoes. So we can have auxetic composites in there as well. Helmets, shin pads. There's lots of different examples where these could be applied. The work which we're doing as well around fit and the prosthesis, there's problems in sport with ski boots, which tend to be stiff and rigid. You can get issues with circulation. If we want more people to be going skiing, particularly as they're old, this is the problem that we need to be solving. And maybe there could be some kind of metamaterial solution which could help here. It could be some kind of conformable material or sensors which detect and then move to fit the individual better. And then a problem with surfing is you have the wetsuits, and we have some materials which are highly durable and really warm, and some which are less durable. So we want to get durability and warmth, and maybe there's a metamaterial solution there as well. So that's just a few examples. A few more related to what I've been talking to. So we have the running shoes, so the degradation of those shoes over time, which can have implications for performance and injury risk. Can we come up with new materials, so new foams or new structures which would degrade less? And then protective equipment. So there's the examples from Todd's work and Charlotte's work, which we've already shown. And there's some products on the market. So there's a helmet here with an auxetic liner, and the shin pad and the knee pad, which I showed you before. But these tend to be just based on the structure, which is kind of extruded in one dimension. Maybe there's other ways which we can look at this. Maybe we can come up with some more advanced materials which adapt or conform to the specific requirements. And then the wrist protectors as well. So wrist injuries are a common problem, as I was saying before, but not many people wear the wrist protectors. And if you look at this one here, with these very big stiff plates on either side of the wrist, it's quite restrictive. It's not necessarily what you want when you're going snowboarding, but maybe there can be some kind of solution which is very flexible and comfortable in normal use, but stiffens and expands and provides that protection when you're falling over. Because it's not just necessarily about the performance, it's about encouraging people to actually use these things. So we talked before about the Auxetic liner. Sometimes we've got the hard and the flexible, and maybe there can be some kind of smart, conformable or adaptive metamaterial, which is positive or negative properties, depending on when you need those properties. That could be a Poisson's ratio, but it could be stiffness or other negative properties. We could have sensors within the socket liner, which detect when it needs to change and causes it to change. Or they could be within the shoe or someone else. It doesn't necessarily have to be a prosthesis. It could be a backpack or a knee protector. Other different devices which adapt to the needs of the individual. Or it could be the other way around, which rather than being driven by the sensor, the material is responding how it needs to respond, and then the sensor is monitoring how it's responding, and then that can feed back into the design of that material or the requirements for other materials. So I'm involved with the International Sports Engineering Association. I was saying before how I'm the editor of their journal, Sports Engineering, and the UK Metamaterials Network. So I think there's opportunities to bring these areas together. One of the things which we're doing is we're looking to have a metamaterials in sport collection within the Sports Engineering Journal. And I think that's a really good opportunity to bring these areas together. And we also have our UK Sports Engineering Seminar Day. We hosted the last one in Manchester. It's a free event. The next one is going to be on the 12th of April in Canterbury Christchurch University. So people that are interested in metamaterials can come along here. We've had speakers on that topic before. So it's a great opportunity to try and stimulate work between these different communities. And also, sport and advanced materials is a great opportunity to empower the public and young people about science and engineering. So that's something that we do. So we have a Royal Academy of Engineering funded project. It's called Sports Shoes, a Feat of Engineering. And we're going into primary schools and we're talking about sports shoe design, the application of metamaterials, 3D printing, and all the things which I've talked about today. And just to conclude, there's a video here which Ollie's put together for the Institute of Physics. that video is on YouTube as well, I think, so you can watch that. Thank you.
So we've already got a question in from the virtual attendees. Ken Evans would like to ask you, would you like to comment on how easy or difficult it is to take products to a commercial scale, for example, timescales, complexities, economics, etc.?
From an academic perspective, it's difficult because that's not necessarily our core area of expertise. And I think it depends on how ready that material is to go into the product. So the work we've done with foams, as I was showing, there's quite a lot of work to create those materials, develop the processes, and then you'd have to work with the company and speak to the company, and they'd be interested in how they can then bring that into their current production processes without too much cost. So that can be quite difficult. The example where we worked with Head was very seamless with a tennis racket, because the key thing about that was we were using conventional materials. So that was quite straightforward, because they could take their original materials, lay them up in a certain way, and then get the auxetic properties. So it really depends, I guess, how close that product or that material is to be used. But usually the companies will want to know, well, what do we need to do to put this into our product?
Are there any questions in the room? I don't know this mic is on. Use the mic, then the.
Yeah, do
that. Yeah, so I think you showed the shoe. I think it was the Under Armour shoe that had the bow tie pattern.
Yeah, the clutch fit. Yeah.
Yeah, I was just wondering, like, so what are the benefits of having that pattern? What is the pattern actually kind of doing to the performance of the shoe in that case?
So I think that's specifically in the upper of the shoe, so the top part of the shoe, which your foot would go into. And I think the idea is that can expand. So if it does that and it expands, it allows you to make the shoe essentially much tighter, and then you put your foot in and it will expand around your foot, rather than, I guess, a traditional shoe, which may be a bit baggier on your foot and might have some areas where it's a bit loose or rubs a bit. This would be tight and then expand around those prominent areas.
No question.
Thanks for your talk. I was just wondering how metamaterials fit into this. Is it your opinion that all auxetic materials are metamaterials, or where does it lie in what the definition of metamaterials comes from?
Okay, yeah. So I would say that auxetic materials are metamaterials, and as a mechanical engineer, I tend to work more in that space. But metamaterials are much broader than what I was talking about today, and I don't want to give the impression that what I was talking about today is the only space where metamaterials could be applied in sport. No, there's lots of opportunities far outside of what I was talking about.
I was wondering how you define or how you determine the correct thickness for the application you're using, particularly, for example, here with this crushing example. What number of cells of thickness is required, or how do you define that? And on top of that, are these types of materials and thicknesses sufficient for particular applications? So you think about shin pads, is it acceptable to use it in its current state?
Okay, yep. So many of the sports will have some kind of regulation for the products, or there could be some kind of standard. Sometimes they specify dimensions, but normally it's about performance. So it has to meet certain performance criteria. And then generally speaking, it's as thin or as streamlined as you can get away with. If you make something that people don't want to use, then it's not going to be useful. The example on the screen, I appreciate, is quite thick, but that was more about validating the model and just looking at sort of I guess an arbitrary kind of shape before then looking at applications. And Todd was particularly interested in helmets, and he was looking at other applications and other shapes later on. But to answer your question, really, it's as minimalist as possible is what people want. Otherwise, they won't use the product. In the running shoe, though, it can be quite thick. The rules changed recently, and there is a limit now on the running shoe thickness, but it's pretty thick. So I think in a running shoe, there's plenty of space. In a shin pad or the liner of prosthesis, that's where it's quite difficult because the traditional foam is really thin. So then you've got issues around performance and making it in that minimal thickness. Theoretically, you could model it and show that it would work, but to actually make it that thin, it's quite difficult.
Yeah, I guess that was the question. Was you've got bulk properties and you assume they're elastic constants, and then you truncate it so it's got an interface, or it's on some kind of rigid backing. It changes significantly, right? So I wondered if everything has to be designed in situ for a particular application.
Ideally, yes. You can't just. I mean, most of what I've shown today, we've taken a material, we've compressed it between two plates, or compressed it with some kind of stud or something like that. If you think about what I was showing at the start of the presentation, so my work before I was working with Andy is more about, okay, so how do we test the sports equipment in the most realistic way? And that's where Andy and I come together. So the wrist surrogate, we've looked at different iterations of that with soft tissue and different shapes and the rugby padding. So originally it was just a rigid anvil and we've put soft tissue on that. And actually even the simple example I'm showing on the screen, that should probably be on top of some kind of soft tissue simulant rather than just compressing it between two plates, because it could behave differently. The friction at the interface, if we're putting some kind of shell on top, how's it bonded? So yes, it needs to be as realistic as possible, but it also needs to be simple so that it doesn't become so complicated that then we have lots of experimental uncertainties. So it's balancing the two. What we try and do, particularly with the standardization, as I was saying before, on the standards committee, is to understand what's going on. And that's where the universities can come in, really understand what the problem is, and then simplify that down to the simplest possible test, which can detect that.
I'll do the final one. On tennis racket comparison, do you take into account the full structure of the racket? So obviously you've got turning moments and so on, but each racket will have its own resonance.
Mm-hmm.
Then you compare, say, the wooden one to the aluminium one, and they perform very differently, but they've changed dimensions drastically over the years. So if you attribute it specifically to the frame material or the combined frame design, each resonant modes.
Yes, yeah. So we're looking at it as a whole object rather than individually, essentially. Yeah. So lots of different things have changed, and we're looking at the overall vibration of the structure. And the big thing is that the mass has changed. So the modern rackets are much lighter as well.
We've got a question from Fabrizio in the chat. Hi Tom, great talk. Are you looking at the characterization of long-term conditioning / aging of the Auxetic metamaterials?
Not currently, but if you think about what I was showing with the running shoes, that's exactly what we do need to be doing. So it's relatively standard for sports companies to do long-term aging of their products, particularly running shoes. So not currently, but yes, we should be. And I think that the companies that we're working in partnership with will be doing that as well, because usually when we develop a foam or a material, we test it and then they test it in-house, run it through their standard suite of tests, and then come back to us if they're still interested.
Fabrizio had put his hand up, so I guess he has a question to ask.
I think that was his question.
Oh, that was his question. Okay. With that in mind, then we're probably in Exeter. We've got people waiting at the door, so we're probably running out of time. So I think it just leaves us to say thank you very much for the presentation today, Tom. Thanks for travelling down to speak to us today in Exeter. And those who are coming to lunch, we will progress up to the common room after this.
Thank you.
Thank you again for your presentation today.
Thank you.
Thank you.